Okay, in this video I'd like to continue the discussion of DWDM system basics. And in the last video I gave you the very simplest picture of a DWDM system with optical multiplexer and optical demultiplexer and multiple channels on the fiber. I also told you about EDFAs. And so what I'll do here is I'll make our block diagram a little bit more complicated, including multiple wave laser transmitters, an optical multiplexer, but then at the transmit side we generally have an optical amplifier posted right after the multiplexer. And then we can put some number of optical amplifiers in the line to boost the optical signal to combat loss. And then finally at the receiver side with an optical demultiplexer and multiple receivers. So essentially what's happened is our fiber amplifiers have solved our loss problem. We can amplify the signal and we're no longer loss limited. But I put the word solve in quotes because they don't really solve the problem. What they do, one thing that they do is they add noise. Okay, so if you have a cascade of these amplifiers, what happens is they're adding what's called ASE noise to the signal. ASE stands for amplified spontaneous emission, and basically through the operation of the amplifier you have a certain amount of noise which gets amplified along with the signal in the amplifier. So if we were to make an OSA plot of the signal, say at the beginning near the beginning of the span, what we'll see is we'll see multiple DWDM channels, and again this is optical power versus wavelength. We'll see multiple channels, and these channels will poke up very high up out of the noise floor. So here we'll have a low noise floor. Okay. Whereas after a few amplifiers, what you'll see is that you can still see these optical channels poking up out of the noise, but we have a much higher noise floor. And the difference between on a vertical decibel scale, the difference between the signal strength and that noise floor is referred to as the optical signal to noise ratio. And so what's happening here is the ASE noise added through this cascade of amplifiers degrades the optical signal to noise ratio. Okay, so a degraded optical signal to noise ratio causes a large bit error rate. And so we're limited, it doesn't really solve the loss problem completely, but to a large extent it does, as long as we don't go so far that our ASE noise destroys our bit error rate. We're now generally getting to a situation where we previously had a loss limited system, and now we're getting to the point where we have a dispersion limited system. Okay, so we know there are these two big things which limit our the span of our fiber optic links, and those two are noise and dispersion. And the presence of EDFA or any optical amplifiers here in this system takes us from loss limited to dispersion limited. Well, how do we fix that? Well, probably the most common way is to use dispersion compensation. And I've got a little example here to show you the idea. Basically, we can make what's called dispersion compensating fiber. And the way we do this is through tricks of waveguide design and index profile design and materials in the fiber. And we can make dispersion compensating fibers with very high dispersion values. And in this example, what I've done is I've taken a 20 kilometer link of SMF28, standard single mode optical fiber, whose dispersion is something like minus 18 picoseconds per nanometer kilometer. And I've taken a very short length, 2 kilometers, of dispersion compensating fiber whose dispersion is 10 times. Okay? And so I've got 10 times the dispersion and only 1/10 of the length, and you can see here in a simple accounting for the total pulse spread, delta tau, I've got dispersion number 1 times length number 1 times the spectral width of the source plus dispersion number 2 times length number 2 times the spectral width of the source. These two spans of fiber have differential delays which simply add. Okay, and so factoring out the constant delta lambda, we have M1L1 plus M2L2, and in this example you can see I've rigged it up so that minus 18 times 20 plus 180 times 2 does give us 0 delta tau. Okay, so we have no dispersion. And so in this case we've perfectly compensated for the dispersion using this dispersion compensating fiber. And this is generally what we do. Dispersion compensating fiber, instead of having just 10 times the dispersion, may have 20 times the dispersion. And may have, and hopefully, if it's going to work, it's going to have the opposite dispersion of our fiber, so it should have positive dispersion. And so what we do is we can take this 2 kilometers and roll it up into a spool, and we make what's called a dispersion compensating module. It's a spool of dispersion compensating fiber that we can put before our receiver and have net zero dispersion at the end. And so this can give us very high bandwidth rate distance products. So R times L product is very large when we get rid of dispersion like that. It turns out with DWDM systems, all the M's are a function of wavelength, and that greatly complicates dispersion compensation. Okay. And basically what you want to do, and what you want to do is make it so that you have the lowest dispersion possible across the range of wavelengths that you're going to use. And generally speaking, the net dispersion of the system, including your fiber and your dispersion compensating fiber, will also be a function of wavelength. Okay, so M net or I should say delta tau net will be delta tau will be a function of wavelength. Okay. And what you want to do is you want to make it so that the zero dispersion wavelength is in the center of that range. Okay. Let me go ahead and try to draw you a picture of that here. So what we're going to do is we're going to draw the dispersion as a function of wavelength, and maybe let's say we're operating on the C band from 1530 to 1565 nanometers. Okay, it turns out that we'll be able to choose the length of the dispersion compensating fiber so that we can make it so that the this is going to be delta tau net now. And the thing we want to do is we want to put the zero dispersion point in the center of the range. Let's put the zero dispersion wavelength at the center of the wavelength range. And why is this? because only the absolute value of delta tau matters. Okay, it's only the absolute value of delta tau that matters in our dispersion. So a positive dispersion is just as bad as a negative dispersion, and as long as you keep the magnitude of the dispersion low, you're doing better. And so if we had put, maybe you can imagine putting the zero dispersion point over at the edge of the range. Well, the maximum, this is delta tau I'm plotting here. The maximum here is much larger than if you were to put it down like this. Okay, so we don't want the zero dispersion point at either side, okay, of the range. We want it to be in the middle. Okay, and that's because this configuration has a maximum dispersion which is smaller than the maximum dispersion for either of the other two cases, which would be either up here or down here. Okay, I hope that, there's my delta tau. Hope that makes sense. And that's just to give you an idea of some of the complications that arise as we try to do dispersion compensation in WDM systems.